Hi, I'm Katherine Dykes. I'm a section head at DTU Wind Energy in Denmark, and I will be presenting today on how we rethink wind farm design and operation and control from the perspective of maximizing their value and their overall profitability in the electricity system. A few years ago, a group of researchers came together to look at our future sustainable energy systems globally. And we thought about, what would it take to actually realize 50% or more of our global electricity supply from wind energy. So we're about 5% of our electricity supply coming from wind today globally. Going to 50%, 10 times the current level of generation, is really a paradigm shift from how the electricity system of the 20th century was formed and organized and operated to the clean and sustainable energy system of the 21st century. Historically, the development and deployment of wind energy has been driven by the fact that the cost of energy, the levelized cost of energy for wind energy, has fallen exponentially, and now wind energy is competitive throughout much of the world globally on LCOE terms with conventional generation. But to keep wind competitive going forward, we of course still need to continue to drive down the costs and keep wind competitive, especially as the costs of other generation like solar and gas continue to fall. But at the same time, there's this realization that as we look at systems where we have 5, 10, 20% or more of the generation coming from wind, that actually changes the dynamics of the operation in the markets for those systems. And there's actually negative correlation between wind energy and prices. And so if wind energy is participating in the merchant market, then it might actually see less revenue in a high wind system than one with a small amount of wind generation. And not only that, as we think about high renewable systems of the future, the grid integration community has hypothesized that the structure of markets in the system may shift in the future from ones that are highly energy dominant today to ones that are capacity and ancillary services or system services dominant in the future. And wind has been less competitive in these markets historically, and so this would really change what it will take for wind to be competitive and continue to be deployed on large scale as we move to higher and higher shares of wind in the system and realize these high renewable share electricity systems. So looking to the future, we can look at the success of wind in two different ways. Firstly, if there's a lot of storage in the system that's very cheap, we have a lot of sector coupling and generation of power to X, green hydrogen, etc. If demand is highly responsive and elastic, then maybe all we need to do with wind is produce cheap electrons. But if the system is heavily constrained and we need to think about having more dispatchable and predictable resource from wind energy, maybe we need to rethink a bit and look at objectives for system design and control that go beyond LCOE. And more importantly, these two things are sometimes at odds with each other. So innovations in design and control that might actually reduce the cost of energy may not increase the value, may actually decrease the value. Alternatively, innovations or system adaptations that increase the value, for instance, the addition of storage, increase the cost, but ultimately may make the wind farm more profitable. So where will the future be? We had a group of around 70 experts come together to reflect on this and try to think about, the innovations that are necessary to actually push to this future high renewable energy system with low cost, high value wind as a backbone. We had over 70 folks meeting in 3 separate meetings, and out of that was an article that we produced on what it will take in the research needed to drive the innovations to realize this high renewables, high wind, and clean energy system of the future. So the grand challenges in wind energy science and engineering to enable a wind-based future energy system. These grand challenges include 3 high-level challenges. The first is focused on the physics of atmospheric flow, so moving from the upper scale atmosphere down through and into the plant. Secondly, the system dynamics and materials of the largest and most flexible machines that have ever been built. And thirdly, optimization and control of fleets of wind plants that are made up of hundreds of individual generators working to support the electric grid. So this is the one that's perhaps of the most interest today, although they're all relevant in terms of how we design, operate, and control wind farms of the future. So firstly, a little bit more on the challenges. Firstly, the challenge around the atmospheric physics of wind. So we have large-scale phenomena at a global level. These cascade down into regional weather systems. Those then in turn affect the flow at the individual plant level, and then there's wakes and interactions of the flow at the plant level, down to the interaction with the individual machine and how it forms and produces the wakes, and how those propagate downstream and affect the other turbines. And we're increasingly needing to look at this as a coupled system. We're no longer able, because of the size of the machines and the scale the physics evolve, to work just within a single scale. We need to look across the scale of physics. And not only that, we need to look at the coupling back from the machine and the plant level up to the atmosphere as well. The second grand challenge is around these large, enormous machines that have to dynamically operate in turbulent conditions for 30 years reliably and compete at the levelized cost of energy as a commodity price for electricity. So we're talking about huge dynamic machines that need to withstand all types of complex loading over their lifetimes, but still be produced and manufactured cheaply, using materials that have the properties necessary to withstand all that loading, but also that can be manufactured and produced very cheaply. So this is a huge grand challenge as we see turbines going to the size of 10 megawatts, 15 megawatts or more, especially for large-scale offshore machines. And then as we add in the additional dynamics of the floating system, we have yet another layer of complexity in terms of the loading and the design and the operation and control of the individual machine. Finally, and unfortunately this video doesn't work on my machine, but we have the integration of these farms making up hundreds to thousands of these facilities that are supporting the electricity grid system across the world. And the flow physics and the operation of the individual machines and control of the individual machines is increasingly a problem that is tied into what's going on the electricity grid side of the connection. So the dynamics for providing ancillary services around reactive power control, voltage control, are linked to what's going on in the farm in terms of the flow physics, how the machines are being controlled and operated, and how those machines are being loaded over their lifetime. So very, very complex challenges. But how does this then come back to how we rethink wind farm design and operation and control for objectives of value, for objectives of profitability that go beyond LCOE? So LCOE is already quite complex. It involves all the capital expenditures, the operational expenditures, the energy production, the aspects of financing for a plant. And it depends on the site and the resource. So, you need to be able to take in the context of the particular site, and all the permitting and the zoning that's associated with that in order to accurately quantify LCOE for a wind farm. But it does not depend on time-varying and market-dependent revenue. And so this has made it nice from a system design perspective, because from an optimization context or a control design context, you don't have to take into account how that revenue is changing over the course of a year or over several years in terms of the operation of the plant. If we want to move towards taking into that system context, there are metrics out there from the economists' side of things that account for system LCOE and other sorts of metrics that take into account the effect of the other generation in the system, transmission, demand, and how all this rolls up into an assessment of the economic performance of an individual asset or plant. But these are very complex and not really well suitable for a design context. System LCOE is difficult to assess because it depends on all the heterogeneity having to do with the system generation mix, transmission infrastructure, demand elasticity, storage, sector coupling, etc. There's huge amounts of uncertainty involved from the system, market, and regulatory side, and this evolves over time. But we can do things by building simple statistical or surrogate models to reflect, how an asset would perform from a system LCOE perspective, but can be a simple enough metric to use in a design or operation or control strategy development process. One metric like this that we recently developed with a team from Virginia with Eric Loth and Juliet Simpson and myself is called the cost of valued energy. It's basically a statistical model relating the revenue of a farm to the level of wind share in that energy system. And so that can change as the level of wind in the system changes. Interestingly, LCOE and COVE will actually drive the system design in different ways, because things like innovations that might improve the cost of valued energy, like high capacity turbines, low wind speed turbines, overplanting, etc., will tend to actually increase the LCOE. So there is a trade-off that you are constantly having to navigate between this metric of value and this metric of LCOE. And what we're doing right now is exploring how both the turbine and plant level design influences these differently, and how using these two different metrics will actually end up with different optimal design configurations or operational strategies and control strategies. So where do we go from here? Well, there's a lot that's needed. There's still a lot of work to do with the grand challenges and exploring all different aspects of wind energy science and engineering. And we need a lot of bright minds to look at that. There's a lot of work to be done on the fundamental knowledge, but we also need to start looking, kind of to this new context of beyond LCOE, and think about, what metrics are needed, how can we develop these metrics, how can we address the complexity of the context and uncertainties, and we need then to look at applying those in the wind farm design context, and also in terms of defining control strategies and operational strategies. And thank you for your time.